So as my first duty, it's my very pleasant task to invite the former president, Jens Marklof, to give the presidential address, and his address is going to be on mathematical models of quantum chaos, and I hope that's not an insight into what's been happening in the last 2 years, I hope. So, yes.
Thank you very much. So we're very excited about all the new developments, quantum computing, AI, and what I wanted to start with is a little reminder and a celebration of one of the, I think, most influential papers ever written in science, and that is Werner Heisenberg's paper on quantum mechanics, written 100 years ago. He was 23 years old at that time. And I have here the original in German. And so I read the paper just now. What struck me is its modesty. Today, when we have discovery, we have to have our impact case studies. We have to shout out how brilliant it is and how it would solve all the world's problems. This paper really strikes me in its modesty and its precision and real clarity. So this is about Heisenberg's deep insight that we should create a quantum mechanics. So the title of the paper is On the Quantum Theoretic Reinterpretation of Kinematic and Mechanical Relationships. We should create a theory of quantum mechanics that only refers to quantities that are in principle measurable. And the reason for that is that before Heisenberg's innovation, the existing quantum theories, due to Bohr, Sommerfeld, and Einstein, really relied on looking at very simple quantum systems like the hydrogen atom that can be where you have a separation of coordinates. It's very simple dynamics, and as he here highlights in that paragraph up here, is that as soon as you introduce much more complex electromagnetic fields, none of these things work. And so his big insight was to devise the new, what we now call quantum theory. It's quite interesting. So Sommerfeld was a supervisor, but he doesn't mention him anywhere. He only mentions the Einstein-Bohr'sche Frequenzbedingung, which means the Einstein-Bohr's quantization conditions. He doesn't mention Sommerfeld, who had an important contribution. So this is sort of a little timeline of the early quantum mechanics. Max Planck, of course, who used the postulate of quantization of the electromagnetic energy to derive the famous black body radiation formula. Albert Einstein, who's often described as someone who didn't believe in quantum mechanics. He actually worked a lot on quantum theory, and I think he believed in it. He just didn't believe in the interpretation. God doesn't play dice was his famous quote, but he was one of the pioneers. In fact, part of his Nobel Prize, I think the major citation there was on his explanation of the photoelectric effect. Niels Bohr, as I mentioned, was able to explain the spectral lines in hydrogen using the very simple quantization condition, which was then extended by Sommerfeld to also allow elliptic orbits just in planetary motion and then quantize those. Then finally, Albert Einstein, before Heisenberg, had already an incredible insight that you could quantize integrable systems that are so simple that the variables separate. So Einstein actually had a very deep insight, which often is now quoted as sort of the first treatise of a more complex class of quantum system. Then, of course, there was Heisenberg. Schrödinger, a year later, invented a different description of the modern quantum theory, and it wasn't clear in the beginning that the two were compatible, but Schrödinger proved that. And then I'd like to conclude with my big hero, Paul Dirac, actually live around the corner where he grew up, and I walk past his house quite often, who achieved something that Schrödinger and those before them didn't achieve, namely a relativistic formulation of quantum mechanics, the famous, as we call it now, Dirac equation, which postulates also antimatter. And so I'd like to highlight the amazing people the London Math Society have elected as honorary members over the history of time. Take a mental screenshot of this if you can, otherwise it's fine. I'd like to play a little game with you. So here we see on the second page of our list, Einstein and Sommerfeld. I imagine already back then there was a question, ooh, should we elect him? Is he too physicsy, or is he mathematical physicsy enough? And I guess Einstein and Sommerfeld passed the bar, but Bohr didn't. If you think there's a typo here, that is not Niels Bohr, it is Harald Bohr, who was a Danish footballer. And I'm pleased to say that I think our new president is a big friend of Danish football after this week's tremendous result of Scotland versus Denmark. So Harald Bohr was not only a distinguished footballer, he played in the Olympic team, and they lost against Team GB in the 1908 Olympics in the final, 2-0. He was also a very distinguished mathematician. Now, the next question is, of all the people on the list, where was Paul Dirac? So I checked, he was a member, and he was nominated on the 8th of November in 1928. So that was the year when he wrote down the Dirac equation, and you can see it up there. Here is his PAM Dirac were nominated for election. And it's absolutely interesting to read through these it's all in our archive. Here is an agreement between the London Mathematical Society and University of London University College, which of course had a close relationship. So very fascinating. And then on the general meeting, a few weeks later, on the 13th of December, 1928, Dirac was indeed elected. Up here are the names of those elected, and here you see Dirac's signature in the book that's just disappeared from the table. So it's always worth, if you drop by the Morgan House, to ask staff to have a look at the book. It's absolutely fascinating. And it's kind of intimidating, the papers that were presented at the general meeting. Here is Watson, a new proof of the Rogers-Ramanujan identities. Mordell read his paper on Poisson's summation formula and the Riemann-Zeta function. So I feel a bit intimidated talking to you today on my little things. But my subject today is to talk about mathematical models of quantum chaos in the spirit of what was in Heisenberg's first paragraph there, saying that if you look at really complicated quantum systems, you can't really solve them. So what can you say? And quantum chaos really started in the 1970s after really spectacular and insightful work on more complex quantum systems. So in the 1950s and 1960s, physicists and mathematicians like Wigner, Porter, Thomas, Dyson, Mehta, Gaudin used random matrices to model complex quantum systems, such as heavy nuclei, and very successfully so. So they could really see random matrix statistics model experimental data. And here's the game I wanted to play with you. I'm going to mention quite a few names in this lecture. See who you think were elected as honorary fellows. We'll come back to that at the end. Who gets most answers right will get a prize from me. Now, after these developments in the 1950s and 60s. Berry and Tabor and also Bohigas and Giannoni Schmit were pioneers in asking the question, well, what if we turn to very simple quantum systems? So rather than looking at multi-body, very complicated settings such as in heavy nuclei, what about one particle systems that we can describe very simply? And the surprising insight from these papers was that we also can find random matrix statistics describing the spectra of these very simple systems if the underlying dynamics is chaotic. And on the other hand, if we look at integrable systems, the spectral correlations will not be described by random matrices, but instead by statistics from a Poisson point process. So I want to explore this with you studying examples that are extremely simple and lead to deep and fundamental mathematical problems. Here are those classic papers, and what you see here on the left is the famous Berry and Tabor paper. The histograms that you see here are the gap distributions of certain quantum systems. So quantum systems, as you know, are described by an energy spectrum. And if they're a bound system, these are discrete energy levels. And what we're looking at here is simply the gaps between consecutive energy levels. And they've plotted the statistics of those, the samples over a big part of the spectrum. And you see that there's an exponential distribution that seems to be underlying this. On the other hand, this 1984 paper of Bohigas, Giannoni, and Schmit, a group in Orsay, did the same experiment for chaotic systems, such as the Sina billiard, and you see distributions like this, which resemble the statistics that you see from random matrices. So, what are we studying here? So let me make this a little more precise. So we have a sequence of numbers, and I think of those as my energy levels, Xi1, Xi2, and so on. And let's assume for a moment, just to explain the basic concept, that this sequence has density 1. That means if I count all elements in the sequence up to t, it should approximately grow like t. Now, we are interested in the distribution of the gaps between consecutive levels. So I'm looking at the difference between Xi(n) plus 1 and Xi(n), and I ask how many of the first gaps of all elements up to t fall in some interval AB, and I normalize just by the total number of elements of my sequence that I take into account. So that will normalize this quantity here to be a probability measure on R. And then the question is, well, will this probability measure have a weak limit as we take more and more elements of our sequence into account? And we will then call the limit measure here the gap distribution of that sequence. Now, another test of pseudo-randomness, if you wish, of a sequence of real numbers is the so-called two-point correlation measure. And that is a bit easier to handle analytically, as you'll see in a minute. And what we do here, instead of looking at just consecutive gaps, I look at the distances between the pairs of all the elements in my sequence. So I look at the pairs Mn of the Xi up to t against some cutoff. Shouldn't be equal because then you'll just count 0. And you ask now again, how many of those fall into a prescribed interval AB? You normalize by t, and that's an important normalization. So you're not normalizing by t squared because the expected number of points that you're having, that you expect to fall into this interval AB is, because our sequence is normalized to have density 1, t. So that's the right normalization. Now, let's test that. And one of our favorite things, that's the Riemann zeta function. what you see here is a famous numerical experiment carried out by Odlyzko already in 1987 on a supercomputer at AT&T Bell Labs. So as you will know, we expect, according to the Riemann hypothesis, that all non-trivial zeros of the Riemann zeta function lie on one line, the critical line of complex numbers with real part equal to 1/2. And what we're looking at here is the gap distribution between the imaginary part of those zeros, imaginary parts of those zeros on the left-hand side. And this is the dots are the numerical data. The continuous curve is a curve that comes from random matrix theory. It's the gap distribution of a large random matrix from the so-called Gaussian unitary ensemble. So just imagine you take a unitary matrix, n by n matrix, so I'm explaining it slightly different, but it's easier to explain. You put Haar measure on that compact group of unitary n by n matrices, and then all the eigenvalues will, of course, be on the unit circle. And so you can look at the gap distribution between those. There's a proof that that will converge as the matrix size becomes large to exactly this kind of distribution here. On the right-hand side, you see the pair correlation function, so the distribution of distances between pairs. We can't prove either of those two things. We cannot prove that the Riemann zeros, the gap distribution for the imaginary part of the Riemann zeros, converges to the random matrix curve on the left, nor on the right-hand side. We know much more about the pair correlation function due to really groundbreaking work of Montgomery, Hedgel, Rudnick-Sarnak, Bogomolny, and Keating. So this has been studied, but I wanted to tell you more about models of quantum chaos. And in fact, this similarity has led quite a few colleagues in both mathematics, mathematical physics, to also think of the Riemann zeros as a prototype of a quantum chaotic system. Of course, there is the old Polya-Hilbert conjecture on can we find an operator that is self-adjoint and produces the Riemann zeros. So there is this kind of observation here, some further evidence that there might be, and I stress might be, a spectral interpretation for the Riemann zeros. So I'd like to now come back to the Berry-Tabor conjecture, which asserts that if you look at a completely integrable quantum system, then typically its eigenvalues should have the statistics of a Poisson point process. So I'm not going to explain to you what a completely integrable quantum system is. If you don't know this already, I'm just going to give you one very simple example that you can explain to a first-year mathematics undergraduate. So we are going to look at a rectangular box in 3 dimensions, and we will solve the eigenvalue problem for the Dirichlet Laplacian on this box. This simply means we look at the eigenfunctions of the Laplacian, requiring that they vanish at the boundary of the box. So we can all do this in a one-dimensional box, right? And the solutions will be sine and cosine functions. And, well, actually, there will be sine functions because they have to vanish at the ends of the interval. And in 3 dimensions, it's exactly the same because everything separates. This 3-dimensional system, because it's a rectangular box, just reduces to the product of 3 one-dimensional problems. So that's exactly where the old Bohr-Sommerfeld quantization comes in. So it's an extremely simple system. Now, if you do the calculation, what you'll find is that the eigenvalues in this setting will be given by the values of quadratic form evaluated at integer points. So this is my diagonal quadratic form here. So this is what the eigenvalues look like, where the coefficients of the form are given by pi squared over the dimension of the box. So the length L1, L2, L3 that defines my box. So that's the answer. And so you think now, how hard can it be to show that the gaps between the values of these values of my quadratic form have an exponential distribution? So let's try to look at this problem. The first question is, well, is my assumption that I have a sequence of density 1 satisfied? And you quickly convince yourself that that's not the case. So if you count all integers, all the values of my form at integers up to t, then it grows like this. Essentially just grows like the volume of the box. Sorry, the volume of the quadratic form of radius t. So here's the answer. So you see that in 3 dimensions it grows like t to the 3/2. So it grows too fast. It's not a constant density sequence. So we have to renormalize it. And this is done by simply defining a new sequence of psi n by taking that growth into account. So I'm now not looking at a form, quadratic form anymore, but I'm looking at the quadratic form to the power 3/2. So that'll be a homogeneous form of degree 3. And we want to now understand the distribution of those values of the quadratic form. So here's a little numerical experiment, and you can see in a few lines of Mathematica you can write an algorithm that produces the histogram of those spacings. So what you see here is simply how many gaps between the values of the form fall into a small bin like this, and so on and so on. I've taken the cutoff parameter, which I called t on the previous slide, to be 100. And that's the result that you see for a very specific choice of box. You can quickly assure yourself that if you were to take a cube as your box, this wouldn't come out because the quadratic form would just produce integers. So all the spacings would be integers. So we'll just have a big peak actually at 0 because there'll be a lot of degeneracies. But for a generic box, and I've picked these very explicit values here, you see that the gap distribution is exactly that of a Poisson point process. So unfortunately, we do not know how to prove this. And this is not just the royal me, but that's anybody can prove this. And some seriously good mathematicians have looked at this problem. However, we can show something about the 2-point correlation function. And this is very recent work with my colleagues Woo-Young Kim and Matthew Welch. And that says that as long as there is a certain condition, an irrationality condition, on the side length of my 3-dimensional box, then the 2-point correlation function, so this is this 2-point measure, converges to the Lebesgue measure. So this is what this theorem here is really saying. So RT is a measure and it converges to the Lebesgue measure because it just reproduces the length of the interval in which you're counting your spacings. And I've written here for the connoisseurs in the audience what I exactly mean by that irrationality condition, kappa Diophantine, and I've written down here what that is, so you can read it in your own time. The condition is very soft. It's satisfied by almost every triple L1, L2, L3 in the sense of Lebesgue measure. But what is something we're particularly proud of is that we can give an example. So Laura in her lecture earlier mentioned that we know things about almost every surface, hyperbolic surface of large genus, but we don't have a specific example. What our theory is able to produce is a specific example of a box for which this Diophantine condition is satisfied. And it's in fact not just that example, but any numbers where the ratios between the side length is an algebraic integer will work. So this proves the Barry-Tabor conjecture for second order statistics for this very, very simple model. And you'll say, well, okay, so what is he talking about? He probably didn't have much time as president, so he's producing some trivial results here. So let me just convince you that, in fact, this is a problem that's related to some very, very deep problems in pure mathematics. Previous results include work by Peter Sarnak, who proved that almost every positive definite binary quadratic form has a percolation function that converges to that of a Poisson point process. This was then extended by his student Jeff van der Kam to quadratic forms in an arbitrary number of variables and also higher degree forms, again, only for almost every. Then a real breakthrough in their fundamental work was that Eskin, Margulis, and Moses in 2005 were able to refine Sarnak's result by giving those explicit examples, just like on the previous slide. And finally, also my own work and that of Margulis and Mohammadi was able to extend such theorems to inhomogeneous quadratic forms, where you, instead of looking at points from a lattice, you look at points from a shifted lattice. And the interest in this problem goes back to an old question related to an Oppenheim conjecture, which in fact also previous President Heilbronn and Davenport were very interested in. And that is the general question about the distribution of quadratic forms, not necessarily of gaps, but simply the distribution. But you realize that if you're interested in two-point correlations, you basically are looking at differences between the same form. So you can reinterpret this as a diagonal quadratic form of signature 3-3, because here we have a positive form in 3 variables. Here we have a positive definite form of 3 variables. So the difference between the two gives you a form of signature 3-3. And we prove a more general theorem, which allows us to count the number of values of this form. And that's the new thing in shrinking intervals. So I'm not going to bore you too much about sort of the technical details, but it's essentially what this function here does, this cutoff function, is restricts the count to integers up to some quantity m. And what we do here is we count the values in an interval of size 1/L, essentially. And well, then we get this asymptotics for a range of L and M. And what is the new thing here is that indeed extends previous quantitative versions of the Oppenheim conjecture due to Eskin, Margulis, and Moses, who could only count in fixed intervals, so when L is fixed. So our theory can use a more wider range, and in particular, for this critical scaling here, our result is the first in 3 dimensions that is able to produce a proof of the Barry-Tabor conjecture under explicit Diophantine conditions. The key elements of the proof was to, first of all, write our counting function in terms of a exponential sum, a Siegel theta function, which is an automorphic form, where the integral, the integral can be identified with a so-called unipotent average, and then we can use dynamical techniques based on Ratner's theorem combined with upper bounds on Margulis functions to prove that that unipotent average over the theta function converges to something, and that something is actually the answer that we want. It's very different from the original approach of Eskin, Margulis, and Moses, who had a direct sort of dynamical systems approach to the lattice point counting problem. And what I find particularly pleasing about this is that it is much closer in the spirit to Hardy and Littlewood's original technique of using sort of Fourier analysis to address problems in analytic number theory. Good. I'll pause here for a second for you to read this. This is really only to give you an impression of the elements of what we're doing in this proof. And using this Fourier analytic approach is indeed the key step that allows us to count also in shrinking intervals. So that was one side of what people are interested in quantum chaos, proving that the spectrostatistics of integrable systems follow the same statistics as a Poisson point process. Now let's talk about models of real quantum chaos, which means we study systems where the underlying classical dynamics is indeed chaotic. And the examples that Laura discussed with us in her beautiful lecture are hyperbolic surfaces. Here's a crash course in hyperbolic geometry. The model is the complex upper half plane that you've seen in Laura's talk. We endow it with the Poincaré metric, which makes the upper half plane, turns it into a space of constant negative curvature. And then we can build compact hyperbolic surfaces by picking a discrete subgroup of the group of isometries. So here's the group of isometries. It's essentially SL2R, so 2 by 2 matrices with determinant 1. We pick a discrete subgroup, suitable discrete subgroup, and look at the quotient of the upper half plane modulo that discrete subgroup. And then if we look at the geodesic flow on the unit tangent bundle of that group, it's one of the most simple examples of a strongly chaotic system, a so-called Anosov flow. So right from the start of quantum chaos, people were interested in these surfaces because they have a very simple quantization. And that is simply, you look at the classical motion, which is a point particle following the geodesic desics on that surface. And its quantization is simply given by the Laplace-Beltrami operator, which I've written up here. And we now look at eigenfunctions that are invariant under the group. So we could, for instance, think about functions that live on the surface. So they should be invariant under the group action. That would correspond to the case here when I choose a trivial character of the group. So that would just mean that the function is invariant under all elements eta from my group gamma. But I can do more, and it'll be fun to also include non-trivial characters. In that case, the functions won't live on the surface, but that doesn't matter. So they'll transform according to this law. And the nice thing is these characters have quite a simple representation in terms of simply an exponential e to the 2 pi I. I haven't defined e here, so e of x is e to the 2 pi I x. So in the exponent, we have a fixed vector theta times the homology of my group element. So the homology is simply the abelianization of eta. And for each character, I have a one-to-one correspondence with a point theta in r to the 2g. And obviously, there is some invariance under translation by integers. So it's really on r to the 2j modulo z to the 2j. And that's it. So that's our eigenvalue problem. And we now get a sequence of eigenvalues, and we'd like to study the gap distribution. And we'd love to prove the conjecture that has been around now for over 40 years. There's a physical interpretation for those eigenvalues with the characters, and that is in terms of the Aharonov-Bohm effect, where you imagine you have magnetic flux lines through the holes of that surface. So good. Why do we like this model of quantum chaos? It's because we have a trace formula that we can use. That's the only tool, really, that is available here, but it's a great tool. We do not have any explicit formulas for those eigenvalues, unlike in the example that I've just studied before for the box, where we knew what the eigenvalues were, namely the values of quadratic forms at integers. Here we have no information, but we have this formula. Here's an algebraic version of this. It's convenient to think of the left-hand side as a sum over eigenvalues, not quite the eigenvalue, but the square root of the eigenvalues. So on the left-hand side, we have sums of this form where h is some test function. Think of it just as a weight function, like a Gaussian, for instance, that truncates the sum. But it's a general function. And then we have here a term that knows about the genus of the surface. And here we have sums over conjugacy classes of the group elements in my group. Remember, gamma was the discrete subgroup that defined the surface. So if you change the surface, you change gamma, and therefore you change what's on the right-hand side here. The first term doesn't change. The genus, unless you change the genus, of course, but for fixed genus, this won't change. And so we have the character appearing here, and we have the Fourier transform of our function, and we have the traces of the elements from my conjugacy class appearing here. So that's a very nice explicit formula. There's a geometric interpretation of the Seelberg trace formula because we can identify the traces of my conjugacy classes with length of closed geodesics on my surface. So we can in fact now think of the first term as the area, because as you've seen in Laura's lecture, the genus is related to the area. So we have that, that's a geometric interpretation. And here it now becomes a sum over closed geodesics. And the remarkable thing is that this looks almost like the original Bohr-Sommerfeld quantization rules. You see, Heisenberg started off by saying we have to forget about classical path of our particles. These we'll never be able to observe. I need to create a quantum theory that only knows about principally observable quantities. And it's quite remarkable that in these very complicated systems, you do see the classical orbits re-emerge in that trace formula. Really remarkable. Seelberg's trace formula is from 56, so it is quite old already. Now, we have a Weil law, which tells us that the number of eigenvalues up to lambda grows linearly in lambda. So this is almost the sequence of psi that we want. Remember, we wanted a sequence of density 1 to be able to do proper statistics of gaps and so on. That's really important because if the gaps would grow on average, then we would compare apples and pears in the lower lying part of the spectrum and the higher lying part. So we need to unfold, and that's what we've done and what we have to do in higher dimensional systems like the box I described to you in 3D. But here it's just a simple linear rescaling by the area or the genus of the surface. So these psi j will now have density 1, and let's see what we can say. One second order statistics that I'd like to discuss with you, which is very closely related to the two-point correlation function, is the so-called number variance, which asks the question, and what's the distribution of eigenvalues in a very small interval as you shift it across your spectrum. And that is convenient here because, as I said, we only have the Seelberg trace formula as a tool. And so all we can really do is count in eigenvalues. And so that's what we do. We design a test function that, in a sense, mimics a characteristic function of a very small interval. This interval will have size 1 over L, roughly. And we simply want to understand how many eigenvalues sit in this interval. There's also a parameter tau here, which determines the position of the interval in the spectrum, right? So tau just basically shifts the interval across. And what we'd like to understand is if we throw down our interval at random with respect to some probability density, do we see random matrix statistics, right? Very basic fundamental question. And The first thing is when you look at a random quantity, so the number of eigenvalues in this randomly shifted interval, the first question is what's the expected value? And that we can work out quite easily from Weyl's law. And the expected value is not a surprise, just the Lebesgue measure of over our test function f. So if f would be the characteristic function of your favorite interval, it would just be the length of that interval. But the real test is now the number variance. And so what we'll do is we take the actual number of points in our tiny interval, we subtract its expected value, square it, and ask, well, what is now the expected value of that mean square? What is the mean square? And as you will now see, well, we have those sums and we can apply Zilberg's trace formula. So if you think about this for a minute, the expected value will be very close to the first term that involved the area. That's from the Weyl law. So really what you have now is just the square of the sums of those closed geodesics of my surface dressed up with these phase vectors. And so we need to analyze the sum. So you'll again say, oh, now we know everything because we know what the geodesics are. Of course, we don't, right? Because they're very, very complicated objects. They grow exponentially fast. And they're extremely hard to analyze. Michael Berry had a very beautiful, insightful, developed a very beautiful, insightful heuristics in the 1980s, where he said, well, okay, we'll look at this double sum and we average it over this spectral interval. So why don't we just make the assumption that all terms except those when my phase factors here are identically zero, everything else doesn't contribute. So this means that either gamma is equal to gamma prime. So we just look in our double sum at the so-called diagonal term where we say, I just take the orbit gamma and itself. Right? Or I take the orbit gamma and its time reversal inverse. This would be gamma prime to the -1. And with that assumption, so you throw away all other terms, you end up with this kind of diagonal sum. This you can now evaluate because we know what is the density of closed geodesics. That's a famous law by Huber from the 1950s and much greater generality proved by Margulis for many, many other anosov flows. So you can work this out. You replace the sum by an integral because you know what the density is. That would be the correct density. And you get an answer which is consistent with what you get from random matrix theory. I'm not going to do you the calculation in random matrix theory. You just have to trust me, right? So that actually was a fundamentally important observation. Now, I'm writing here GOE and GOE. These are essentially two different random matrix ensembles that in this famous conjecture of Bohigas, Giannoni, and Schmit were associated with systems that have time reversal invariance and systems that don't have time reversal invariance. And in fact, Berry's analysis gives us the right answer in both cases. The choice of characters that we have can be thought of as either preserving or breaking time reversal symmetry, and indeed you get the correct answer. So you get the right answer that matches the prediction from random matrix theory. So that's quite significant. There was follow-up work by Sieber and Richter, quite spectacular, who also understood or developed a heuristics how you can take this beyond this diagonal approximation by identifying partner orbits of this type, so the dotted orbit and this figure 8 orbit, and then there were higher order correlation terms, which actually remarkably produced the full random matrix expansion. So the only problem is we can't prove anything in this direction. Completely hopeless, because there are exponentially many other pairs of orbits that we've just thrown in the bin and neglected, and there's no justification for doing this. So being pedantic pure mathematicians, will say, well, let's try to try something else. And this was inspired by an old paper due to Aurich and Steiner, who observed that if we start averaging over moduli space, so we don't just look at one fixed surface, but we start averaging, the statistics emerge much, much faster. So this was a numerical observation where instead of just looking at one surface, they look at 12 surfaces. You know, mind you, this was from 1990, where computer power was nowhere near what it is today. So you just got much, much better agreement with random matrix theory, as you see here, by averaging over the surfaces. So that's what we want to do. And I will have a look on the president and tell me when to stop. Still a bit of time? Good, thank you. So you've seen in Laura's talk on how to start with a surface and then deform it. That was her big bag of random surfaces. And we're just now gonna average over those surfaces and see if we can establish random matrix theory this way. Again, this is a slide for the connoisseurs which shows on how do you do this in a mathematical way. You start with your model surface of a given genus G, and then there is a way of generating the so-called Teichmüller space of surfaces. And then, as Laura described to you, there is some invariance, so there are some diffeomorphisms which give you the same surface, and this would be the mapping class group. So you mod out by that, and then by some miracle or amazing insight, you actually can put a mapping class group invariant symplectic form on the space. This is a famous work of André Weil and Peterson. And that form also gives you a volume form, which in fact transcends to a finite measure on the moduli space, which is the Teichmüller space modulo the mapping class group. So since it's finite, you can normalize it to be a probability measure, and you then have the notion of a random surface, and in other words, something you can average over. Okay, so in a beautiful paper by Z.F. Rudnick 2 years ago, he indeed was able to show that if you take that number variance function, but now rather than doing a spectral average, you throw your window down at a random point at the spectrum of the surface. We don't do that. We just fix that interval, and we just throw our surface at random. What Rudnick proved is if you take that object, the number variance, you take first the limit of high genus, and then you make your interval small, you see random matrix statistics emerge. This is a limit that is quite at the far end of what we're actually trying to prove, because it is not testing eigenvalue correlations on the scale of the mean separation between those eigenvalues, but at a very, very extreme other end. But nevertheless, quite remarkable that you get this distribution. Now, the key steps in Rudnick's proof were again to use Zilberg's trace formula, then realize that the contribution of so-called simple pairs, which means that both closed geodesics. So I'll just remind you here that the Zilberg trace formula is a sum over closed orbits, closed loops on your surface, and here we have a sum over pairs because it's the number variance, so it's second order, so we have a double sum. So he realized that the contribution of simple pairs can be realized as a Mirzakhani geometric function, and Mariam Mirzakhani, in the work that Laura referred to, provided us with integration formulas for such geometric functions. So Rudnick used her integration formulas to work out the contribution of these simple pairs, in particular the non-separating pairs, which give the leading order contribution. And by some miracle, you get the answer of random matrix theory. All other pairs Rudnick could prove rigorously yield lower order contributions. So this is really the first ever rigorous proof that the spectrum of large hyperbolic surfaces have anything to do with random matrix theory. I think that's fair to say. There was an open question though, and that is, you see here, Rudnick got the answer for the GOE distribution. What he wasn't able to do is to prove the same for systems without time reversal symmetry. And that's where Laura and I thought, oh, we can do this. And so the key, I would say, innovation of what we've done is that we extended Teichmüller space to also include the characters by a semi-direct product construction where the mapping class group acts on the characters, or rather the thetas that define the characters through the symplectic group. That's well known. And then in this sort of semi-direct product construction, we were able to now throw the surface at random and consistently at the same time also the characters. And we did not only allow for the thetas to be sort of randomly distributed, uniformly distributed with respect to Lebesgue measure, but we could also put these discrete measures localized on rational points. Key was the invariance under the symplectic group, which you can convince yourself here. So this is basically a finite sum of irrational points with denominators q, normalized in such a way it's a probability measure. And this then gives us an extended Teichmüller space and an extended moduli space for the surface and its character variety. And then using similar arguments as Rudnick, we were able to prove that indeed you can also get other statistics. So not just the GOE statistics describing time reversal quantum systems, but also those with broken time reversal symmetry, because once you switch on that character, it destroys the time reversal symmetry. And the proof goes very much along those lines, except we are no longer dealing with Mirzakhani's geometric functions, but what we call length holonomy functions. But then Fourier analysis in theta allowed us again to reduce this to Mirzakhani's integration formulas. We could also deal with Dirac operators. Again, our friend from Julius Road next to my house. And here, the prediction of random matrix theory is that under certain symmetry conditions, you should see certain Gaussian symplectic random matrix statistics. And indeed, we could recover this with a similar construction. So that was very pleasing, I think, and to see really random matrix theory observing there, or emerging there, and being able to prove some rigorous statements about it. But it's still wide open. So for instance, we would love to be able to take these limits jointly. So here we really need to first take the genus to infinity and then L large. We really would like to do this as a joint limit to get anywhere near the relevant range for the original conjectures by physicists. Now, I'm going to conclude now, and I'm going to come back to my little quiz. Who are the people that I've mentioned here you think were elected as honorary fellows? Any suggestions? Wonderful. First prize. Anyone has two names? Margulis, very good, very good. Say again? I didn't mention Sine, and I should have. Oh, I did mention him where? Did I mention Sine? Okay, I missed that myself. I didn't pay attention to my own talk. Thank you very much. Okay, good. So here are the answers, and I should then also correct Sinai. So we had Poincaré, Hilbert space, André Weil, of course, genius, the Weil-Peters metric, Maria Mirzakhani, so that's on page 1. On page 2, we have more. Hadamard appeared in the ensemble, Weil's law, Siegel theta function, Zilberg's trace formula, Dyson random matrix statistics, Sarnak, who worked on the quadratic forms, and of course the great Margulis, who was elected last year. Thank you very much.